Hello, this is Mladen from Group E6. Our group is composed of Neve Byrne, Niall Robinson, Shannon Victory, and myself, and we were given problem number 6, entitled Group Rearrangement Probability. I will use this scratch animation done by Niall Robinson to explain what it is. Basically, you have two unlabeled teams of n members each, so in this case n is 3. And when these members are taken out of their teams and then rearranged at random, the question is, what is the probability that there will be k swaps? So in this situation, we can see that there's only one swap. C swapped with F, right? They're on two opposite teams. But what if B also swapped with E? So we have dem 2 over here. How many swaps is there then? Your logical thing to say is 2, but it's not, because the teams are unlabeled. It doesn't matter if they're on this side or on this side, because C and B would still be on the same team. The only fishy not on their team is A, that wasn't their team last time. So technically there's still only one swap. That is basically our problem. Okay, now as for the solution of the problem, before I get into our formula for the solution, I'm going to go through some of the formulas we created and used inside our solution for simplicity's sake. The first formula I'm going to go through is NCR. Now, NCR is a popular formula in probability. It's basically telling you I have n amount of people, and I want to know exactly how many ways they can be arranged into groups of R. So here's the mathematical formula that we found on this source, and that transformed into C++ code is on this source. We did not come up with any of this ourselves. Okay, so this is the maximum k formula, and basically what this means is it's a formula that returns the highest possible swaps that could happen for an individual n. So, for instance, if n was 4, you could have 0 swaps, you could have 1 swap, you could have 2 swaps, but you can't have 3 swaps, because 3 swaps is actually 1 swap, as explained in the explanation of our problem. So it's very simple formula. It's basically it checks if n is even, and if it is, it returns n divided by 2, or else if it's odd, it returns n minus 1 divided by 2. Okay, so the max combinations formula is another formula that we came up with ourselves simply by looking at simulations. And basically what the formula is it gives you a number of the total possible outcomes you can get after rearranging a group of n people. And the formula goes like this. It's NCR of n times 2 n divided by 2. Now, the reason we have NCR n times 2 n is if we have, for instance, if n is 4, that means that there are 8 individual people. And we have to find a way to take these 8 individual people and make them in groups of 4. Now, the reason it's divided by 2 is because if we have A, B, C, D as one group and E, F, G, H as another group, that's the exact same as E, F, G, H and A, B, C, D. See, that's why we divided in 2, because if we didn't divide it in 2, it would record both of those instances as individual outcomes, which they are. Alright, so here are these simulations I've been talking about a lot. Basically what we did is we got together as a group and we made a C++ program to simulate our problem for us. So in other words, it would have two groups of n members. So it would have A, B, C, E, F, G. It would take out those members and rearrange them randomly. For example, E, B, C, A, F, G. And then what it would do is it would record this outcome as a unique outcome, and it would also record the amount of swaps that happen in this outcome. So in this case it'd be 1. So for instance, if this happened but then AFG EBC happened, it would not record this because this outcome is basically the same as this outcome. So it wouldn't record this. And it would do that about 10 million times until for about the first 7n here. And then what it did is it would output the total unique combinations that it found, so the total unique outcomes that it found, and also for each k, how many of these combinations were 0 swaps, or 1 swap, or 2 swaps. So for n equals 4, there was a total combinations of 35, and out of those 35 combinations, 16 combinations happened where there was only 1 swap. And then based on this data, we found most of our formulas. For instance, the formula for the total combinations, it was n times 2 NCR n, so divided by 2, so that's 8 NCR 4, which is 70, divided by 2, which is 35, which in the end made logical sense to us, as I described in the last slide. and also the formula for the combinations for each n. So that happened to be n NCRK multiplied by itself. So we'll do an example of this. So we'll say 7 NCR maybe 2 is 21. Multiply that by itself is we get 441. So that's it. This would work in every circumstance other than if n is even and it's the very last simulation, which makes sense. So we'll try that now. So 6 NCR 3, but this time rather than multiplied by itself, it multiplies by half of itself. So 6 NCR 3 is 20. Let's multiply that by half of 20, which is 10, and we get 200. Okay, so here we have our actual algorithm done in C++ for our solution. So we have max combinations algorithm is used, the maximum k algorithm is used that I explained beforehand, and then we have the amount of swap combinations. Remember I described this in the simulation results. So it's NCK, and then over here, depending on if n is even and if it's the last k, it will either multiply by itself, as so, or multiply by half of itself. Then over here, this is just getting rid of impossible circumstances, such as if k is less than 1, or if k is greater than maximum k, or if n is less than 2. And then here's just returning the amount of swap combinations divided by the total combinations. And that's our algorithm in C++. Okay, so just as kind of a proof of concept, here I have a program version of our solution where you input n and you input a k, for instance 2, and it gives you the probability of that circumstance. And here is a simulator that I wrote where you give it an n and a number of simulations, like for instance 10 million, and that takes its time, and yeah, you'll see when that's finished. And just as our simulator is coming to an end here, you can see what it does is it runs 10 million simulations, and then for each simulation it sees the amount of swaps there has been compared to one solution or one output, and it tells us that 2 swaps happened 49.3% of the time out of these 10 million simulations, and we predicted that it would be 48.7. So we're fairly close, and we're fairly confident in our solution of the problem. This has been Mladen from Team E6. Thank you very much.